Hey class, we're going to do 8.6. This one is on de Moivre's theorem. I've been practicing that pronunciation. It's a French mathematician, de Moivre's theorem. And powers and roots of complex numbers, which is what you use the theorem for. There's the theorem. It's basically a generalization of the multiplication of two complex numbers. Now we're taking any complex number to the power of n, so where n is a positive integer. And we have this nice little formula. So let's do an example. Again, if you want to see the proofs of the theorems, please check out the videos in Pearson or in the textbook. There's some good ones about where it comes from. But again, it uses addition and sum identities and generalizations of the product of two. Blah, blah, blah. Okay, let's get to an example. So just follow that structure of that theorem and you're going to be in good shape. Right? Notice n appears in three places. N is always the power. So in this example number one, there's n, right? And so just plop that in where it says to do it. So you're going to take the 4, this front 4 to the power of n. So that's 4 to the 4th. And then cosine 4 times 30 plus I sine 4 times 30. That. Okay. So that really saves you a lot of time, this theorem, because if you didn't have this theorem, you would have to do a lot of foiling, right? Multiplying that thing out by itself 4 times. It'd be an algebraic nightmare, but now we have something we can handle. 4 to the 4th power, I can calculate that. That's 256. And then we got cosine of 120. I sine 120. And then this one's rectangular form. Okay, so we're going to take this a little further, just use the unit circle, right? What's the cosine of 120 in exact value? That's negative 1/2. The sine of 120 is positive √3/2. Distribute and you've got your final answer. So 256 times 1/2, half of 256 is 128. And then so I'm going to get plus a 128. And we're going to write that I√3, like that. Final answer. We've got it. Okay, so there's the idea of this de Moivre's theorem. Next, let's try another one. Okay, so the power is 3. So the n is 3. I'm going to have 5 to the 3rd. If you are getting tired of writing cosine plus I sine, you can always try that cis notation. And then you just write 3 times 90 degrees. Cis stands for cosine I sine. So this is 125 cis 270. 3 times 90. Okay. And then rectangular form. So cis 270 means cosine 270. Unit circle on that. Cosine of 270 is 0 plus I times sine of 270. Sine of 270 is negative 1. Have your unit circle handy for these if you don't have it memorized. And then multiplying this out, we have 125 times I times negative 1. That's negative 125I. And that's the final answer. Okay. Oof. Here we have rectangular form to the 8th power. All right. So again, if we're going to use the theorem, we're going to have to convert that first to trigonometric or polar form, right? So I'm going to find r. Right? So this is like going back to the last section. R is the square root of 1 squared plus √3 squared. Right? So that's just using that formula from the previous section, 8.5. and that's going to be square root of 4, which is 2. R is 2. Everything is positive here, which is nice. So I don't have to worry about anything but quadrant 1. So I can just go straight to my tangent formula, right? Tangent theta of b over a, or root 3 over 1, y over x, opposite over adjacent. If you want to draw it out, that might help, but I just plug it right into the formula from 8.5, and then I get my theta. Theta is tangent inverse of root 3, which is equal to 60 degrees. Okay, so 1 plus I root 3. I'm ignoring that power of 8 right now. I'm not even worried about that yet. I'm just converting that inside the parentheses to trig form. Is going to be 2 cosine plus I sine, right? Or cis 60. Okay. Now I'm going to take that to the 8th power. So 2 cis 60 to the 8th. I take the 2 to the 8th power, and then the 60, I multiply it by 8, right? And a reminder, cis, cosine plus I sine, okay? Just using that shorthand notation. All right, so this is going to be 256, 2 to the 8th power, cis 480, okay? And now you got to think of cosine of 480, which is the same as cosine if I subtract off a 360. So this is going to be equal to the same as the cis. You can subtract off a 360, get a coterminal angle. That's 120, right? It's 256 cis 120. Whoa, we just had that. That's right there. Okay, so 256 cis 120 is the same and got the same thing. That's going to be the negative 128. So just refer to example 1 for the rest. 128I root 3. Okay. All right. So if it's in rectangular form, convert to polar form first and then apply the de Moivre's theorem. And you've got it. Okay. Finally, we're going to get into some nth roots of complex numbers. All right. This is getting crazy, right? So an nth root, what is an nth root of a complex number? It's a value such that if you take the complex number to the nth power, you get that value, right? So you know roots, you know nth roots just by real numbers, right? Like for example, 3 to the 4th power is 81, right? That's a fact. What you can say then is that 3 is a 4th root of 81. Right? So the notation, the lingo here, the wording, 3 is a 4th root of 81. Right? So if you take a number to the 4th power to get 81, then that number is called a 4th root of 81. Now it turns out if you're dealing with the complex number system, there's always the same number of roots as the root you're talking about, right? So if we're talking about find all the 4th roots of 81, there should be 4 of them if you include complex numbers, right? So I know 3 is 1, negative 3 is 1, right? Because negative 3 to the 4th power is 81. And there's a couple of complex ones that I don't really know what they are, but there's a formula for it, which is a manipulation of the de Moivre's theorem, which is right here, okay? Now, this is in the extended form. It looks like, whoa, craziness, but there's K's and N's. And okay, so N is the root, right? K is a counting number. You're just going to be plugging in K's. And then we know what the R and the theta is. They're the same as before, okay? So another way to write this one, and it's going to be helpful to keep the writing down. You can do that cis notation instead of writing cosine plus I sine, just do cis. and then just write one of those. Whoa, what did I just do? Let's just back that up. K360 is what I tried to write, and I didn't. Okay, so that's the way I'm going to be writing these, is that cis notation. Okay, so example, find the cube roots of that thing. Here we go. So what is my n? You know, n, because it's cube roots, is 3, right? And then there's my theta, 180, and my r is 27. So write this thing. I'm going to have r to the power of 1 over n cis cosine I sine theta 180, and then plus the k, just leave it k for now, all over n, which we know is 3. Right? So n appears in 2 spots. Okay. Now I know that I should get 3 answers. It's cube roots, n is 3. There should be 3 of them. Okay. So one way to do this that's going to be helpful is, let's just take this one step further. 27 to the power of 1/3, or it's the cube root of 27, or what times what times what is 27. So that's equal to 3. Right? 27 to the 1/3. You can use your calculator, just type it in, 27 to the power of 1/3. That will give you 3. Cis, and then what I'm going to do with this is I'm going to break it up. I'm going to take 180 divided by 3, which is 60, and then times k 360 divided by 3, 120. This will be more useful when I start plugging in k's. It'll be easier. Right? So I just broke it up into 2 separate fractions and reduced. Okay, now we're going to start plugging in k's. Always start with 0 and just keep on going until you have the number of answers you're supposed to. In this case, 3 answers. So if I plug in k equals 0, I get 3 cis 60. If I plug in k equals 1, I get 3 cis, okay, 60 plus 1 times 120 will be a total of 180. And then one more. If I plug in 2, 2 times 120 is 240, plus 60, 300. And those are my 3 answers. I could leave them like that, that's trig form, or we could take it a step further and write it in rectangular form. It just depends on the question. So you might be done there, or you might have to go to rectangular. Let's just do rectangular for practice. How about 3 cis 60? What would that look like? So that'd be 3 times, what you're going to do is cosine of 60, which is a half. So that's all unit circle stuff. And then sine of 60 is root 3 over 2. So I times root 3 over 2. Okay. So those are the same thing, just 2 different forms. And then you can multiply the 3 throughout to make it look a little better. Okay. That's the rectangular form. 3 cis 180, it's 3 times the cosine of 180, which is -1, plus I sine 180, which is 0. So this would equal just -3. And then the 360, let's practice that one. Cosine of 300 is positive 1/2. Sine of 300 is negative root 3 over 2. And then distribute the 3. I would write it 3i root 3 all over 2. There would be the rectangular forms of all of those. Okay. So either way, trig form or rectangular form, just whatever the directions call for. One final thing we can do with this problem is graph it. So each of those can be graphed on the complex plane, And the cool thing is that, okay, let's just draw it out here. I draw a little X, Y, imaginary axis, real axis, and then draw a circle. Okay, this circle has a radius of 3 because my R is 3. So that's +3 there, -3 there. All of these values, all of these complex numbers as vectors are going to appear inside that circle. So for example, 3 cis 60, let's do these in red, would be starting at the origin and going at a 60-degree angle out to 3 units. -3 cis 3 180 would be right on the negative real axis. And then 300 degrees is down here. Right? So that's the 3 cis 60 there. That's 3 cis 180. And that's 3 cis 300. And notice they're all 120 degrees apart. And they all have the same radius going out to that circle of radius 3. So pretty neat to graph. And that's always going to happen where they have this kind of cutting up a circle into equal parts feature, I guess. Okay, so I'm going to stop there for now, and we'll come back and finish off this handout with some more examples. Okay, hope it's making some kind of sense, and send questions my way if you have any. Thanks. Bye.